This glass tube is closed on one end and open on the other end. We are going to take some metallic mercury, a very dense element, and fill the tube until it overflows. Next, we will invert the glass tube and put it into a dish of mercury so the bottom of the tube goes under the surface. We can see that the mercury has dropped from the top of the tube. If we hold one end of a meter stick at the surface of the mercury in the dish, we can see that atmospheric pressure holds up a 76 centimeter or 760 millimeter column of mercury.
So as the video shows, if you take a glass tube, closed at one end, open on the other, and fill the tube, which is about 1 meter long, with mercury, then clamp your thumb over the open end and lower the tube into a pan of mercury, not all the mercury stays in the tube. Some falls out, and consistently you get a column around 760 millimeters high of mercury that stays in the tube. Now, what causes this? Before Torricelli, the existing idea was that there was a vacuum in the tube inside here, and it was the vacuum that held up the column because nature abhors a vacuum. But Torricelli just didn't buy that explanation. It just didn't seem right to him. He'd had some training in hydrostatics, and he knew that since the time of Archimedes, he knew that water pressure is a function of the depth of water, not the volume of water. So if you add water to two connected tubes, and one of those tubes is thin and the other fat, the water will come to the same level in each as an equilibrium is established. And Torricelli understands that air has mass, and therefore it's not that there's a vacuum in here that's holding the column up, but rather there's a pressure from the atmosphere on the surface of mercury in the pan, and that pressure is what's holding the mercury up in the tube. Torricelli wrote, "The force that holds that quicksilver against its nature to fall down has been believed hitherto to be inside the vessel," the vacuum in other words. "But I maintain that it is external and that the force comes from without. On the surface of the liquid which is in the basin, there gravitates a mass of air 50 miles high. Is it therefore to be wondered that the mercury enters and rises to such an extent as to come to equilibrium with the weight of this outside air which presses upon it? We live submerged at the bottom of an ocean of the element air, which by unquestioned experiments is known to have weight." So around 1640, Torricelli had devised the world's first barometer, which is still used today to measure air pressure. Still, there are skeptics of Torricelli's theory, one who claimed that it couldn't possibly be right because the column did not fall when one placed a dome over the apparatus, supposedly protecting it from the air pressure. Torricelli countered that one hadn't changed the air pressure simply by covering the assembly, that you would have to pump the air out to see the mercury column fall. Others would have to test his prediction because the air pump hadn't yet been invented.
Here we have a shorter column completely filled with mercury and sealed at the top. The lower end of the tube is open and is submerged into a dish of mercury. In the 1600s, Torricelli boldly theorized that atmospheric pressure was keeping the mercury column up. He thought that enclosing the apparatus in a chamber, then pumping out the air, would cause the mercury level to fall. Torricelli didn't have an air pump to test his hypothesis, but we do. Let's begin pumping out the air and see what happens. As the atmospheric pressure drops, so does the mercury level in the tube. If we turn off the pump and open the system to air, watch the level of mercury rise as the pressure in the chamber increases. The air pressure once again pushes the mercury back into the tube.
Well, now we're going to look at another device for measuring gas pressure. It's called a U-tube manometer, and it is very simple. It is basically a glass tube in the shape of a U, and it's filled with mercury. And one side of the tube is connected to the system in which there's a gas whose pressure you want to know. The other side is the tube that is open to the atmosphere. So when the two levels of mercury are equal to one another, and if the outside atmospheric pressure were 755 torr, what would be the pressure within system A? And most of you, I suspect, would correctly say the pressure inside would be the same as the pressure outside because the levels of mercury are equal and there's no unbalanced forces pressing down on the mercury on either side, so that you know the pressure inside equals the pressure outside. By the way, 755 torr, the word torr is of course short for torricelli, and it stands for millimeters of mercury. Millimeters of mercury, that's what torr means. So let's look at a different system now, all right? What if we have system B, and in system B, it looks like this. The side connected to the gas system whose pressure we're measuring is lower than the side that's open to the atmosphere by a difference of 34 millimeters. So right off the bat, let me ask you, would the pressure inside system B be greater or less than atmospheric pressure of 755 torr? And if you can visualize the gas pushing down on the mercury here, while on the side open to the atmosphere it's pushing it up, it has to mean that the gas pressure inside system B is greater than 755 torr. So the difference is a 34 millimeter difference that would be greater than 755. So the pressure inside the system would then be 755 plus 34, or 789 torr. All right, let's look at another. So now in this system, the inside tube connected to the system is higher than the side connected to the outside. And the difference in levels is 28 millimeters. So you can imagine then that the gas pressure inside is of lower pressure and it's pulling up on the mercury, whereas the atmospheric pressure is pushing down to account for this disparity in height. So the pressure inside has to be less than the pressure outside by a difference of 28 millimeters, and therefore we would determine that by simply subtracting the 28 millimeters from 755 millimeters of mercury, or 755 torr, to get 727 torr. Well, the reason we explain how a U-tube manometer works is we're going to use one right now to show you what happens to the pressure of a gas when we change the temperature of the gas, either by heating it up or cooling it down, to make a plot of temperature versus pressure of a gas system. And we'll be using a U-tube manometer to determine what the pressure is. Let's watch.
With this apparatus, we will try to observe any relationship between the temperature of a gas and the pressure which the gas exerts. This round-bottom flask is connected via a tube to one side of a U-tube manometer. The pressure in the flask can be determined by measuring the difference in levels of mercury in the two sides of the U-tube. If we connect the apparatus, now at room temperature of 25 degrees Celsius, we note that the levels of mercury in both sides of the tube are equal to each other, both at 30 centimeters. Let's record this data so far. Now we light the Fisher burner and allow the water to come to a rolling boil. We see that as the pressure begins to increase, the levels of mercury in the U-tube become different. Eventually, we can see that the mercury reads 39.6 centimeters on one side of the U-tube and 20.4 on the other side. Thus, the difference in levels is 19.2 centimeters or 192 millimeters of mercury. The pressure in the flask is 192 millimeters greater than the pressure in the room. Next, we restore our original system, but this time pack the flask in ice water. We note immediately that the pressure in the system begins to drop. After equilibrium is established, we note the levels of mercury are 6.4 centimeters or 64 millimeters apart. Summarizing our data, if we divide the pressure for each trial by the temperature in Kelvin, we obtain the same values. This pressure-temperature relationship is a direct relationship. As the temperature increases, the pressure increases proportionally. And as the temperature decreases, the pressure decreases proportionally. This relationship is more strikingly seen when graphed.
So we have a direct relationship between pressure and temperature, which is expressed as a straight line. And do you remember in high school you were given the equation for a straight line? Y equals mx plus b. So we can apply this equation to this straight line. This is a direct relationship. Pressure is increasing as temperature increases. When we plot it, we get a straight line. And the equation for a straight line is y equals mx plus b. But let's cast this equation for a straight line in terms of the parameters that we have here, pressure and temperature. Then we'd have something that looks like this. Pressure equals K instead of M times T plus B. Now, what about these terms K and B? Well, K, which was M in our equation up here, K, we know, is what? The slope of the line, right? So let's remember that. We'll talk more about that in 1 second. But B is what I want to talk about right now. B is the place where the line crosses the y-axis. And the value of y at the point where the straight line crosses the y-axis. That's what B is. All right? So what would have happened if we didn't convert to Kelvin? If we kept the temperature as Celsius, then here it is crossing the y-axis, and the value of B when we use Celsius is no longer 0 as it is when we use absolute temperature, because at absolute temperature it crosses the y-axis when the pressure is 0, and therefore the value of B is 0. But if we kept it as Celsius, it would cross the y-axis way up here, and the value of B would be around, what, 600 or so. It would complicate the calculation quite a bit. So we put it in terms of Kelvin, and we get a direct straight line relationship right to a hypothetical absolute 0, 0 temperature at 0 pressure. Then our equation looks something like this. P equals KT plus 0. That's if we use absolute temperature, because B then is 0. And if we solve for K, K equals the pressure divided by the temperature. So for this direct straight line relationship, pressure divided by temperature is equal to a constant K, which is equal to the slope of the line. Providing, of course, we convert Celsius degrees into Kelvin, or absolute temperature. Now let's do an experiment where we change the volume and we see what effect that has on the pressure of a gas.
With this apparatus, we will demonstrate the relationship between the pressure of a gas and the volume which it occupies. This is a syringe connected to a U-tube manometer. When the volume is 50 cubic centimeters, the levels of mercury in both sides of the tube are equal to each other. Both are at 28 centimeters. This means the pressure in the syringe is equal to the pressure in the room, atmospheric pressure of 760 millimeters of mercury. Let's record our data. Now we push in the plunger of the syringe to a volume of 45 cubic centimeters. We see that the levels of mercury in the U-tube become unequal. The higher level is 30.5 centimeters and the lower level is 24.5 centimeters. The pressure in the syringe is 6.0 centimeters of mercury, or 60 millimeters of mercury greater than the pressure in the room. This means the pressure in the syringe is now 820 millimeters of mercury. Let's continue in this fashion. As we bring the syringe to 40 cubic centimeters, we note a pressure difference of 170 millimeters, which brings the total pressure to 930 millimeters of mercury. And if we squeeze the syringe to 35 cubic centimeters, the new pressure can be calculated as 1,038 millimeters of mercury. If we multiply the volume of each trial by the resulting pressure, we obtain very similar values.
So let's take another look at the data that we've generated with this volume versus pressure relationship. When the volume is 50 cubic centimeters, the pressure is 760. When the volume drops to 45 cubic centimeters, the pressure rises to 820 millimeters. A volume drops to 40 cubic centimeters, pressure rises to 930. So what we see is that as the volume gets smaller, the pressure increases. Now we call that kind of relationship an inverse relationship. One parameter is going up in value and the other is going down in value. Now when we plot these data, and I've thrown in a couple of other data points here at 30 cubic centimeters and 25 cubic centimeters, a curious thing happens. The inverse relationship displayed on the graph does not give a straight line. Can you see that on this graph here, what we have really is kind of a curve, hyperbola. That's how inverse data is represented on a graph. It's not a straight line relationship, starting up and going in a straight line going down. Instead, it is a curve. So just as an example, let's provide you with a perfect idealized inverse relationship, okay? Here we have x and y. When x is 1, y is 1. When x is a half, y is 2. When x is a third, y is 3. So you see we have this perfect inverse relationship. And if we graph this relationship of x and y, it looks like this, a curve. But is it possible to linearize this relationship? Scientists like straight lines. They like being able to use y equals mx plus b. Is there a way to convert this curve of an inverse relationship into a direct proportional relationship? Is there a way to linearize this curve into a straight line? And the answer is sure there is. All we need to do is to invert one of the axes. So I'm going to invert x. So x was 1, it's still 1. But when x was a half, we invert that, x becomes 2. When x was a third, it becomes 3, etc. And now if we plot 1 over x versus y, like we have over here, again, now we have a perfect straight line relationship. So if we apply this idea to pressure-volume relationships, well, we know slope is rise over run. And if we plot pressure versus 1 over the volume, then the slope of the line, rise over run, will be pressure, rise, over run, which is 1 over v. Now, this is a complex fraction. If I multiply both the numerator and denominator by v, I end up with K equals pressure times volume. So when we have two variables multiplied by each other equaling a constant, that is an indication of an inverse relationship. In our direct relationship between pressure and temperature, when we figured out the slope, we learned that pressure divided by temperature is equal to the slope, or the constant. So summarizing, for the pressure-volume relationship, which is an inverse relationship we just looked at, pressure times volume is equal to a constant. For the direct relationship between pressure and temperature, pressure divided by temperature is equal to a constant, another constant. And if we studied the relationship between volume and temperature, with pressure being held constant, that too, like pressure and temperature, would be a direct relationship. So volume divided by temperature would equal a constant. So all of these laws or relationships of parameters can be combined in something called the combined gas law. The old pressure times the old volume divided by the old temperature is equal to a constant K, and the new pressure times the new volume divided by the new temperature is also equal to that same constant K, and because these two things are equal to the same thing, they are also equal to each other. So now we have the combined gas law relationship. So let's try out our new equation with this problem. A gas has a pressure of 750 torr, a volume of 3.6 liters, a temperature of 34 degrees Celsius, what would be the new temperature at 4,500 milliliters and 1.2 atmospheres. Now the first thing you should notice right off the bat is that here you have 750 torr, okay, as the pressure, the old pressure, and here you have a new pressure of 1.2 atmospheres. So either you have to convert torr to atmospheres, or you have to convert atmospheres to torr, but they have to be the same units on both sides of the equation. Also, here you have 3.6 liters and 4,500 milliliters, same thing. They both have to be in the same units. And of course, degrees Celsius must be converted to absolute temperature. So if we do all that, we get our equation, then we plug in our old pressure, old volume, old temperature. Here I'm using the 750 torr, the 3.6 liters, the 307 K after converting 34 degrees Celsius to Kelvin. And note, by the way, it's not degrees Kelvin, it's just Kelvin, absolute temperature. But then I've converted my 1.2 atmospheres to 912 torr. How do I do that? 760 torr equals 1 atmosphere. So if I multiply 1.2 atmospheres by 760 torr divided by 1 atmosphere, I end up with 912 torr. And of course, 4.5 liters is 4,500 milliliters. And then I calculate my new temperature, and that will be in Kelvin. And I convert that back to degrees Celsius by subtracting 273. So that's how you do the problem using the combined gas law. So far we've discussed pressure, volume, and temperature, but there's another parameter that must be considered when we study gases, and that is the amount of the gas, the number of moles of the gas that we're talking about. What would be the relationship of moles to pressure and volume and temperature? We have a tank of gas and a valve, and when I open this valve, gas is going to stream from the tank into this chamber. Now, this bar down here is a piston head, and there's a constant pressure on it, so that this demonstration is going to occur at constant pressure. And as we add moles of a gas to this chamber, what do you think is going to happen to the bar? Well, let's run it and find out. Okay, so here we go. So we're adding moles of a gas, and as you can see, the volume at constant pressure is increasing. So the more moles we add right here, the more moles of gas that we add, the more the volume will be at constant pressure. This is a direct proportional relationship between volume and moles. But what would be the relationship between pressure and moles if volume was fixed and we allowed the pressure to change? Well, this demonstration doesn't show that, but you can just imagine what would happen if now I have the volume fixed here. I don't allow this piston head to rise anymore, and I pump more moles of gas into this chamber. What do you think is going to happen to the pressure? Well, the pressure, is due to the molecules of gas striking the sides of the container. And the more collisions with the sides of the container, the more force there will be per unit area on the sides of the container, and therefore the greater the pressure will be in the container. So if I pump more moles of a gas in, but don't allow the volume to expand, then the collisions with the walls of the container are going to just increase, and therefore the pressure will rise also. So the graph will look very similar to this, with a direct proportional relationship between pressure and moles. So just to review, how do moles of a gas relate to the volume of a gas at constant pressure? They're proportional. The more the moles, the greater the volume will be, just like this kid blowing up a balloon. How do moles of a gas relate to the pressure at constant volume? If you lock down the piston so it can't move, then the pressure is going to build up directly proportional to the number of moles of gas that you put into the system. Another relationship involving gases was formulated by Avogadro, who said equal volumes of gases at standard temperature and pressure, or STP, contain the same number of particles. STP means standard conditions of temperature and pressure. So standard temperature is 0 degrees Celsius and standard pressure is 760 torr. Now, if you think about this, this is kind of a strange thing to say. I mean, here you have hydrogen molecule, very small, and 22.4 liters of it contains 1 mole, 6.022 times 10 to the 23rd particles or molecules of hydrogen. And here's oxygen, a much larger molecule, occupies more space, but again, 1 mole of it occupies the same volume, 22.4 liters, under standard conditions of temperature and pressure. Well, how can this be? Doesn't the size of the molecule have anything to do with the volume that the gas would occupy? The answer to that is no, for gases, because gas particles are very far apart, and the total volume of the gas is negligible compared to the total space that the gas occupies. So therefore, it doesn't matter what the gas is. Actually, it does, but for an ideal gas, it doesn't matter what the gas is, because the volume of the gas itself, the gas molecule itself, is negligible. So 1 mole of any gas under STP conditions is 22.4 liters of volume. So how would we do this question? Countless experiments have shown 1 mole of any gas occupies 22.4 liters. If you had 8 grams of oxygen gas at STP, what volume would it occupy? So we have 8 grams of oxygen. Converting the 8 grams of oxygen into moles, we divide by the molar mass of oxygen molecule, 32, and we get 0.25 moles of oxygen gas. And we know at STP, 1 mole of any gas is 22.4 liters. So if we multiply by 22.4 liters, moles will cancel out. We'll be left with 5.6 liters of oxygen gas. So that would be the volume occupied by 8 grams of oxygen gas at STP conditions. Now we can use this relationship between moles and liters of a gas to convert from the molar mass of a gas to its density, or vice versa. For example, argon has a molar mass of 40 grams per mole. So what would be the density of argon in grams per liter at STP? So our target unit is grams per liter. We're given grams per mole at STP. So since we're given the grams already, and we're trying to find grams per liter, really all this question involves is converting 1 mole, because 40 grams per mole really means 40 grams per 1 mole. So our task is to convert 1 mole into liters at STP. So if we do that, we simply substitute in, for 1 mole, 22.4 liters. Then it's 40 grams divided by 22.4 liters, 1.8 grams per liter. So that's the density. Well, that's fine, but what would happen if the conditions were not at STP? How would we do it then? For example, suppose the question was this. Argon has a molar mass of 40 grams per mole. What would be the density of argon gas in grams per liter at 790 torr and 373 Kelvin? So we're not at standard conditions of temperature and pressure anymore. What would we need to do? Well, we know that 1 mole of any gas at STP is 22.4 liters. So to get to this question, really what we have to answer first is, what would be the volume at 790 torr and 373 Kelvin? If at STP it's 22.4 liters, what would be the volume at 790 torr and 373 Kelvin? Well, we could use our combined gas law, old pressure times old volume divided by the old temperature equals new everything. So here is our original 760 torr, our 22.4 liters, our 273 Kelvin equals the new pressure, 790 torr, the new temperature, 373, and we solve for volume. And we find out the volume under these different conditions is 29.4 liters. That's what 1 mole of a gas equals under these conditions, 790 torr and 373 Kelvin. So now the molar mass is 40 grams per mole. We know under these conditions the volume for 1 mole is 29.4 liters. Replace the 1 mole in the 40 grams per mole. Replace that with a volume that 1 mole occupies, which is 29.4 liters, and we find a density of 1.4 grams per liter. Now there's something you should realize in doing problems like the one we just did, relating moles of a gas to PVT parameters. We're always going to be relating moles, pressure, volume, and temperature at STP conditions. 1 mole of any gas equals 22.4 liters at 760 torr and 273 Kelvin. So the old pressure, the old temperature, and the old volume are embedded right here in our STP conditions. So can we make a shortcut? Can we, since we're always going to be relating to these parameters here of 1 mole, 22.4 liters, 760 torr, and 273 Kelvin, can we wrap these all up into one, super constant? And the answer is sure. Here is the equation. PV divided by NT would equal R, the superconstant. And why do we have it written this way? Because, well, pressure times volume, that's an inverse relationship, so we would multiply those two together. But moles is a direct relationship to pressure and volume, so we'd be dividing by moles and we'd be dividing by temperature. So what we're going to do is embed these four parameters that we always relate to in doing a question like this and embed them all into R to give us a super constant. So here we go. PV over NT equals R. So we enter in 760 torr, 22.4 liters, 1 mole, 273 Kelvin. That equals R. Solve for R. It's 62.4 liter torr per K mole. Now, the one thing is that if your R value is 62.4, and your question asks something other than liters or torr or Kelvin in the numbers it provides, you have to convert into liters or into torr or into Kelvin, because the units that go into this in solving a problem, we're going to do one in just a minute, have to be the same as the units of your superconstant. Suppose you used atmospheres. Another common way pressure is expressed is in atmospheres, and standard pressure in atmospheres is 1 atmosphere. It's the same as 760 torr. So if we substituted in 1 atmosphere, 22.4 liters, 1 mole and 273 Kelvin, we solve for R, we get 0.082 liter atmospheres per K mole. So you get to select which R you want, and yes, both of these constants are going to be given to you at the back of any question, any test involving these kinds of issues. So what I'd like to do now is go back to this problem that we just solved. Argon has a molar mass of 40. What would be the density at 790 torr and 373 K? And solve it with the ideal gas law instead of the combined gas law to show you how much easier the ideal gas law is when we have problems involving moles. You would use the combined gas law if the problem doesn't involve moles. If the problem does involve moles, you want to use the ideal gas law. Because of the superconstant R, the whole thing goes much more quickly. So let's use our PV equals nRT, and we would plug in for pressure 790 torr. We're solving for the volume of 1 mole under these non-standard conditions. So V is our unknown. 1 mole, 62.4 is the value of R when we use torr, and 373 is the non-standard temperature in Kelvin. So we solve for volume and we get 29.4 liters, which is exactly what we got doing it the old way with the combined gas law, but a whole lot faster. So what you want to do, again, if the problem involves moles, you use the ideal gas law, PV equals nRT. If the problem just involves a change in parameters of pressure, volume, or temperature, and moles is not a player, then you would use the combined gas law, PV over T equals PV over T. Well, let's do a question here and solve it using our new superconstant, okay? And our new shortcut equation, which is called the ideal gas law, by the way. If 0.385 grams of a gas occupies 2.15 milliliters at minus 73 degrees Celsius and 750 torr, what is the molar mass or the molecular weight of the gas? So we have the grams of the gas and we have these parameters for the gas. Can we calculate molar mass from that? So our target unit is grams per mole. Molar mass is grams per mole. So here's our shortcut equation for doing this, the ideal gas law, where pressure, volume, and temperature are the new non-STP conditions. And R contains all of the parameters at STP. Well, what we're going to do is solve for N. We're going to plug in 750 torr. We're going to plug in 0.215 liters because remember that R is expressed as liter torr per k mole. So that means our volume must be in liters. And the question is giving it to us in milliliters, so 0.215 liters. And also with temperature, we cannot use degrees Celsius. We must convert to Kelvin. 273 plus a minus 73 is 200 Kelvin. So we plug those all into the ideal gas equation. We solve for N, the number of moles. And now all we need to do is divide the grams by the moles to get the molar mass. So 0.385 grams divided by our calculated number of moles, 0.01292 moles, get 29.8, or rounding off to two significant figures, 30 grams per mole, the molar mass of this gas. Let's do another one now. How many milliliters of 1.99 molar HCl are required to react with an excess of zinc to produce 2.23 liters of hydrogen at 808.4 torr and 27 degrees Celsius? Well, since this is a chemical reaction that's happening, the very first thing you have to do is write out the reaction equation. So if you balance it, you'll have HCl, 2 moles of it, plus 1 mole of zinc yields hydrogen gas and zinc chloride. So there is your relationship, your mole relationship between hydrogen gas and hydrochloric acid. It's a 2-to-1 mole relationship. So now we can use the ideal gas law, PV equals nRT. Pressure is 808.4 torr, and volume is 2.23 liters. We're trying to find the number of moles of hydrogen gas produced. Our constant of all constants is 62.4, and our temperature is 300 Kelvin. That would be 27 degrees C plus 273. So solving for N, we get 0.0962 moles of hydrogen gas. Now we know the moles of hydrogen, but we're trying to find the volume of the HCl. And we're given the molarity of the HCl. That's moles per liters. So if we know the moles of HCl that are going to be reacting, we can use the molarity and the moles to calculate the milliliters. So we've got the moles of hydrogen, 0.0962, and it's a 1 to 2 mole relationship between hydrogen gas and HCl. In other words, we need twice as much HCl as we have moles of H2 being produced. So we write that out. 2 moles of HCl are in the numerator. 1 mole of H2 is in the denominator. Moles of H2 cancel out. And there's our moles of HCl 0.192 moles of HCl. So we take our moles of HCl and we take the ratio provided by the molarity, 1.99 moles of HCl per liter of solution. And we invert it because we want liters or volume to be in the numerator. We want moles of HCl to be in the denominator, so that when we multiply this ratio by moles of HCl cancel out and we're left with liters, which is easily converted into milliliters, 96.7 milliliters. So that is how you'd use the ideal gas law to solve a question like this.